So, hello everyone, good evening to all of you. So, during the last meeting, just power got disrupted, and because of that, I am recording this video after that discussion hour. So, what we discussed during the session was like we discussed basics of GPS, which you already covered in the week 6 content, and then some of the numericals on it, and as well as some of the numericals from gate examination as well. So we are going to do that today in this particular doubt session, or you can say problem solving session. So let's get started. So this particular week is focused on GPS. So when you heard about GPS, it is a global positioning system which is useful for the position, navigation, and measuring the velocity. So when we talk about any kind of positioning system, the first thing which comes to our mind is GPS, because it's a very first positioning system which we had in the world, provided by the NASA, which was already known at that time, now star GPS. So that is very common name, and in general, if we want to say, then we can say it is satellite based navigation system, because we are using the satellites for the navigation purpose. So here, as you can see on the right hand side of the slide, that so many constellations are there, and you can see so many satellites are moving in this space. And on ground, we can see at a time how many satellites are visible. That is being shown by the red color. Uh, red color. So when we want to classify this satellite-based navigation system, we can classify it into three different ways. So the first way is the global navigation satellite system, which provides the coverage all around the world, which includes the GPS from USA, GLONASS from Russia, Galileo from China, BeiDou from China, and Galileo from Europe. And then we have regional navigation systems such as our own IRNSS, which is Indian Regional Navigation Satellite System, or you can also say it as Navigation with Indian Constellation. And then we have quasi-zenith satellite navigation system, which is like QZSS from Japan. And then we have satellite-based augmentation system to augment the whatever the satellites which are there in the sky or space, so to augment those to their particular locations, or to give the navigation system in our aeroplane and all. We have this satellite based augmentation system which gives the corrections basically. So in that we have three: Gagan, VAS, and IGNOS. So now let's get forward. So here you can see that various satellite based navigation system, their owners, their years of initialization, how much coverage they are having, and you can see their orbital altitude is around 19,000 to 20,000, around approximately in that range. Some of the regional satellite are also like geostationary satellite, and they are at altitude of 36,000 kilometer as well. And here you can see the period. So most of the satellites which are like covering global, they are covering like entire earth two times in a day, whereas this like it's like Navig is having just 23 hours, so it's like having period of one day. And you can see that how many satellites they are having in that constellation. That's a GPS is having 32 satellites, where GLONASS is having 24, BeiDou is having 35 satellite constellation, Galileo is 24, and Navig 7 satellites. And then their frequencies, which electromagnetic spectrum that they are using in their operations. So here we are using the L1, L2 in GPS, L3 in GLONASS, B1, B2 in E5 in BeiDou, and so on and so forth. And then there is a status of those satellites, whether it's operational or not. So now we will learn more about our Indian regional navigation satellite system, which also known as NAVIC, which means navigation with Indian constellation. So as you can see here on the right side of the figure, that it has 7 different satellites. Out of that, three are geostationary and 4 are in geosynchronous orbit. And they are covering the region of India. So the primary region of this particular service, let me start my pointer. So here you can see the primary region is the India and the approx 1000 or 1500 kilometer outside the India, which is the primary zone where we have its accuracy is around 20 meter in the primary service area, and then we have this secondary service area. And this particular constellation provides two types of service. One service is in standard positioning service, which is like open for civilian use cases, and the other one is the restricted service, which is useful for the military purposes, which is like encrypted with their own codes, and that because of that, that is like useful for the military operations. So now when we see about the architecture of any GPS system or the satellite navigation system, it is divided into three different segments. The first segment is the space segment, which includes the satellites and the orbit in which they are moving. Then the second is the control segment, which includes the different stations located on the Earth, which are also known as the master stations or monitor stations or ground antenna, which have the communications with the satellite. They monitor the health of the satellite and do the other operations as well. So here you can see, if we see the space segment and control segment, that you can see this green and violet line. So we can send the signals from control segment to the satellite, as well as we can get the signals back from the satellite as well. It means it is a two-way communication which is happening between these two segments. And when we see this third segment, which is the user segment, when we have our GPS receiver at our end or located with us, so in that case, you can see just one line is coming from this satellite to the receiver. It means we are only able to receive the signals. We cannot give the signals to the satellite. It means it shows that one-way communication which is happening between the space segment and user segment. Now, when we talk about in detail the space segment, then this Indian constellation of satellite navigation system has total 7 satellites which are operational as of now. And you can see their type of orbit, then their unique identification number along with their longitude and inclinations as well. And then their launch date and their launch vehicle. So now here you can see that how the satellites moves as per their timing, and like how it, you see. So here you can see that the three are geostationary, so they are not moving that much. They are like at constant locations. When if you see the another satellites that they are moving across their orbit. So here you can see that as of that particular time, around 4, 5, 6 satellite was operational, were operational. And you, if you want, if you are interested in like looking out how they are moving and how many satellites are available if you are at some locations, so that will be helpful in planning the surveys. So you can visit this particular site, GNSS planning. So we'll look into it. So this is one site from Trimble GNSS planning, where you have to provide the locations where you want to do survey. So right now I will put my own locations where I am right now, and then along with that I will keep the date at which I want to do survey, and then I just apply. So then after, if you go and check out which constellations you want to use. So let's say I want to use this GPS constellation, which is here. So it has having right now 31 satellite, GLONASS 24, Galileo 25, BeiDou 48, and QZSS 4. So after that, you can go to satellite libraries. So you can also see their satellites, whether it's healthy or not. And if you click on any particular satellites, it will give the parameters of that particular satellite in detail, clock parameter, then the location of that satellite. So eccentricity, everything you will get over here. if you click on any of these satellite, and then you can go to this charts, and then it will show you the how many satellites are visible at that time, what is the elevation angle of those satellites, and this DOP values, which we will discuss later in this particular lecture. And then if you click on the sky plot, then it will show you the like radar kind of map, where like you are at center and you can see that how many satellites from different segments are passing through you, and which are also available in your area as that particular time. And then if you click on world view, you can see those things over here, and you can make the animations out of it as well. Like if you click over here, then it will start showing the movement of the satellites, that how it will move. So this is all about the space segment of the GPS. After that, if we will move to the control segments. So in the control segments, it's responsible for the maintenance and operations of this IRSS constellation. So basically, it sends signals to the satellite and it receives the signals from the satellites as well, which consist of various navigation centers, then the spacecraft control facilities, then range and integration monitoring system, and then code division multiple access ranging stations. So CDMA, code division multiple access. Then we have laser ranging stations and data communication network. So these are all are the part of the control segments which communicates with the satellites as well. Then we have the user segment, which is consist of the different kinds of receiver. That receiver might be a single frequency receiver or the dual frequency receiver. Single means we are just using one particular wavelength or the frequency of from electromagnetic spectrum, where in dual we are using two different, let's say L5 and S band we are using simultaneously, which will help us to remove some kinds of error that we will discuss in the this particular lecture. So then after we see that we also should have some receiver which is not compatible only with the IRNSS, but it should also have compatibility with the other satellite based navigation system as well, so that it should have, it capture the like signals from the major number of satellites. So that's why you should have like more like it should have more ability to capture the signals from various satellite constellations. Now when we see the applications of GPS, then it can be used under any for any applications which is under sky, which requires the like positional navigation and timing of any particular object. So like what, where that object or phenomena is happening, then how it is changing. Let's say we can see the example of cyclone. So at which location cyclone started, and then navigation means how the cyclone is moving, and timing it means how much time it will take to travel from how much time it will take to landfall, or let's say we can also say how much time it will take to come from the ocean to land or some other state or district, to avoid the infrastructure damage or to provide the risk assessment. So we can do that kind of applications. This is just example of cyclone, but you can think of applications on agriculture, aviation, environment, marine, then public safety and disaster relief, which we discussed, then railways, recreational activities like camping and all, then we have roads and highway, space application, surveying and mapping, and the application related to the time. And here we will see some of the detailed applications as well, such as like if we have reservoirs with us, and if we want to see whether the particular reservoir is deforming or not because of the water, or if we want to measure the risk associated with the reservoir so that we can avoid the flashiness in the release or sudden because of the breaking of the reservoir. So what we can do is we can put our GPS receivers there, and we can continuously monitor the particular bridge or reservoir, and then based on that we will take the initial position and the position after 5 year, or position after 1 year or 1 month, whatever our temporal resolution we want to do. And then we will find the velocity by just taking the difference between the readings and then dividing it by time. So like that we will find out the velocity of the particular locations, and we will find how much displacement is happening and how much time it will take, or how much pressure that water is exerting on the reservoir, or or dam, like that we can study. Apart from that, you can also do this kind of study on the various bridges as well. Then we can do the when we do the oil exploration or some other expeditions. So for that also it will be useful for locating the particular expedition location properly. Then we have the navigation in rivers or ocean, it will helpful. Then we have learned about this photogrammetry and then other techniques where we are measuring the earth or mapping the earth through various satellites and the sensors, or like space borne sensors. So in that also, like if we have GPS inbuilt, we will get the geo-referenced image, which will like automatically overlap on the exit part of the earth. Otherwise, it's just taking a picture. So we cannot put it on map where is it from exactly from. So GPS allows us to do so by automatically georeferencing all the images which we are capturing. And then we have some other applications for the recreational purposes. So now when we see this concept of GPS, it is like we can explain it using the two different ways. The first one is a phase pseudorome. So basically observables means whatever the readings which we are getting from the satellite. So it is just a number that how much distance is there between satellite, that geometric center of the satellite, and the geometric center of this particular receiver. So in the first way, and the first method, which is phase pseudo-range, there what we are doing is we are counting the total number of cycle. Let's say this is the one complete cycle, then this is the second complete cycle, then this will be third one, fourth one, fifth one. So like we will find out how many total number of complete cycles are there, and we'll multiply it with the frequency or like wavelength which we are using, L1 band or S band. So it will give us the distance between this receiver and the satellite. Now, in case if we have some fractional cycle available at the end, so that is known as a phase difference, and that phase difference we will calculate in terms of wavelength, and we will also add that for the calculations of the phase pseudo range. Now, second way, what you can do, you can send a signal from satellite and we will receive it at the receiver, and we will find out how much time it took to travel from satellite to receiver, and we will find the time delay, which is, let's say here we signal is from the satellite at time t and it receives at the receiver end at the time unit of t plus 3. So if we take the difference of it, then it is a 3 a difference of 3 unit. So which means that if we now divide like multiply it with the speed of light, we will get the distance between satellite and receiver is 3 times the speed of light. Then we have the so this, by using these two ways we can find out the what is the distance between the satellite and the receiver. Now, how to find a location of user if we have observable from one particular satellite. So in that case, what we can do is like we have this observable from one satellite, two satellite, three satellite, and four satellites. So if we take from two satellite, then it is like the intersection will be like one particular rounds. Then if we take three satellites, then the intersection of three spheres will be like two different points. And then like if we take the four, then we will just get two different points, like from which like one point will be like on ground and one point will be like on space. So we will consider the point which is on earth, and then according to that we will find out the location of the user. So this procedure is also known as analytical dissection, or we can also say it is a trilateration, where trilateration is a process where we know the distance between the two points, and based on that we are finding out the location of the user. Now here, if we want to model this particular situation, then how can we do that? So this is known as a range between the receiver and the satellite. For jth satellite, and then we can see I is a subscript used for the receiver. So from j satellite and I receiver, and at time t, what is the range between those two? So the first one is the observable which we are getting, which is known as delta, which will be like the distance between the receiver and the satellite. So which is like x minus x naught square, y minus y naught square, z minus z naught square. and under root. So this we will directly get from the satellite. So it will send us and we'll measure it according to the earlier two way which we discussed, code pseudo range or phase pseudo range. Afterward, these two are the delay which is occurring because of the clocks in the receiver and the satellite end. So receiver clock error, which will like if we multiply whatever the error is there, if we multiply with the speed of light, then we can correct it for both the errors. So these two are representing for the satellite clock error and then receiver clock error. So both is there, and then you can find the final, like if you want to find the solution of that equation, like we have four different satellites, so we can find make a four different formulas, and here you can see there is under root is there. So to solve it like linearly, we can convert this thing into Taylor series, and then we can do the maths, and then we can put any function like this fx plus x naught, which is like fx plus delta x into del f by del x plus delta x square by 2 factorial del square fy. So like this we can expand the function. So here we have the function of range, which is a function of your x naught and delta x, so that we can do something like this, which is a function of x naught, y naught and z naught from the user, and then we have this clock errors. So here we are just considering the clock error because of the user, because of the receiver. We are not considering the errors because of the satellite, because that is very less. So we are considering only one as clock error. Then we have this. So we can put it like this, and then it will be converted into the four different equations, which will be like uh, delta rho 1 is equal to a11 delta x a12 delta y a13 delta z plus c delta z. So like that we can get the n number of equations depending on the satellite's visibility. Then we will use this system of linear equation we will get, that we will solve using the least square method, where we will like put the delta rho is equal to b delta x, where is the b is the matrix of all these coefficients. And if we find the solution of it, then it might be written as b transpose b inverse b transpose delta rho. So this will be the solution, and this part b transpose b is also known as a DOP, or the dilution of precision. Now, this is like we will get the final user position. But when we see the GPS, like what is happening between the GPS and user, so what kind of signal it is sending and what we are receiving at the upper end. So there is need to understand like how they are communicating and what they are communicating. So basically, when we take any GPS signals, it contains three different things: carrier wave, spreading code, or also known as ranging code, and then navigational data. So at the end, the superimposition of all those three data sets will be like look like this, that we are getting at our end. So the first one is the carrier wave. Carrier, from its names only, it suggests it carries something. So what does it carry? So it carries the navigational data of the satellite, as well as the spreading code or ranging code, which is the unique identifier for the given satellite. So this spreading code or ranging code is a unique identification. And then this navigation data is the data related to the satellite parameters, then the XYZ coordinate of the satellites, and the observables which we are getting. So now we will see those things in detail. So first, if when we talk about the carrier waves, then it will be classified into three different ways: L1, L2, and L5, depending on what frequency of GPS we are using. So L1 is for civilian use, L2 is restricted for military purposes, and L5 is a new range which they introduced in the recent years. So we can see the frequency of L1 band is 1575.42 megahertz, where the L2 frequency is 1227.60 megahertz, and for L5 it is 1176.45 megahertz. And we can see the wavelength is ranging starting from 19.05 centimeter to 24.48 centimeter for L5. And then the signals can pass through the clouds, glass and vegetations, but it cannot pass through some of the solid objects such as buildings, mountains or tunnels if we have, so it cannot pass through it. And what information it carries is like it carries the first thing is pseudo random code, which is PRN code, which is like unique identification of any GPS satellite, and it is all already like fixed stored into the GPS receiver also to match the to find the time delay. Then we have ephemeris data, which is the data related to the satellite health, which shows the whether the satellite is healthy or not, its current date and time, and so on and so forth. And then we have almanac data, which is the data related to the orbital information for that satellite and for every other satellites which is there in that constellation. Like if we have the example of ISRO's IRNSS, so we can see there are one satellite, and then along with that our other six satellites data it will also give us. Then location of each GPS satellite at any time throughout the day, and each satellite transmit this almanac data sets. So then we have this ranging code or spreading code, which is a unique identification pseudo random number. So it is a binary sequence in terms of 0 1 or something like that, and 0 0 0 1 1 1 something like that. So pseudo random indicates like that code is apparently random for all the satellites, although it has been generated by means of known process. So providing its repeatability. So when we want to send some signals which is like repeatable, so we will construct a signal of 0 1 0 1 0 1 or something, and then after we will repeat it for different times, so that when we get that at the receiver we will match it with our database, and then we can find out the time delay in our signal. And then various kinds of this ranging codes are available, which is PY code, which is for unauthorized user, or code for principal navigation purposes. Then we have this course acquisition CAPRN code, which is like very general for all the applications. Then we have L2CM, which is L2 civil L2 carrier waves. It is applicable, and then it is for civil purposes and moderate frequency we are getting into that. And then we have also L2 civil long code and I5 and Q5, which are introduced in the recent years along with the L5 carrier waves. So like this, we are getting this PRN from satellite. That PRN we will match with our receiver, and then we will find like the common point, and then we will see how much time difference is there between these two, and then the time difference we will multiply with the speed of light, which will give us the observable, and that observable is known as a code range. So here, like there is another way that we are getting this signal from the satellite. So what we will generate the different replicas of the signals which we have at our end. So we'll generate some late replica, prompt replica, early replica. So by shifting it here and there, and then we will see the cross correlation with which replica it is matching well, and then based on that also we will find the time delay based on this correlation. So now this we'll see in detail about this ranging code. So the first one was like P1 or PY code, which is like available for both the carrier waves L1 and L2, and it is a very long sequence of about 10 to the power 14 pseudo random binary biphase modulation on the GPS carrier, which repeats itself every 37 week. And each 1 week segment of this P code is unique to one GPS satellite, and is like reset at each every week it is being reset. And this CA code and P code both are like rotated by 90 degrees, so that is also known as a quadrature phase quadrature to each other. So then after this CA code, which is applicable like available with L1 frequency only. So the earlier code was available for both the frequency L1 L2. Then the next one is available just for L1 frequencies only, which is generated at the rate of 1.023 million bits per Mbps speeds, and then it is 10 times slower than P code. So that's why like we can use for high precise applications P code, military applications, because it's like more faster compared to the CA codes and applicable with L1 and L2 as well. And then satellite specific codes are unique and 1023 bit CA code. And then complete CA code pattern repeats itself at every 293 kilometer between the receiver and satellites. So the repetition is very high in this CA code. Then we have this navigational data. So along with carrier waves and then this ranging code, the third component was the navigational data, which we are also getting along with the GPS signal. So that contains the data related to satellites, then coordinates, then down system data, and we will get long message from the satellite end. So which we will discuss later on using the real life applications. So then we have some terminologies related to the GPS. Such or one of such terminology is selective availability. So selective availability is the like defined by the defense department. So what was there in selective availability is that they will for like we can use the GPS signal for only for like some of us only can use it. So it is available, but for selective purposes or selective users. So that's why they have already introduced the error into it, which will they have included something which gives us the error while calculating our distance user positions. So that distance like errors we show using the standard deviations from the actual position, and you can see because of this selective availability we are getting the 30 around 30-meter errors in our position, finding our positions where they they removed this after the 2000, so we do not have any selective availability afterward, but earlier it was there in the initial years. So basically, if we want to summarize the signals which we are getting, then each of these three civil GPS signals has one or more their advantages. According to application and their advantages, we can use it for our application. That L1 frequency and CA code has the lowest ionospheric error. So that is the ionospheric error is the biggest error which we are contributing, which is contributing in the GPS satellite when we find out any user location. It is the biggest error which is affecting our data. So to remove that, we are using L1CA code. Then L2C code has like the best cross correlation performance, and then L5 has high power and it can penetrate through trees and canals easily. So that's why it is like more useful for the high-end application for aeronautical radio navigation system service and so on and so forth. And then thus each signal will be like prevalent in its domain and strain. So according to our applications, we can use it. So now, when we talk about now, we are comfortable with the what is the GPS, what is the different components of GPS, then what GPS carries, and then how to find the location of user using the GPS signals. So after that, we will see now like what kind of errors can be introduced in the GPS. So for that, like both carrier phase and code pseudo range, both are can be affected by several type of error, which is like random errors and the systematic error. Random error, which is like generating because of any reason, because of human reasons, or because of the topographic variations, or some of the nearby object, which we cannot model. Whereas the systematic error, which we can model it easily and we can remove it from the observations. This error may be classified as a those. So we have three segments. So when we talk about GPS, so the first segment is the space. So error can be introduced in the space. So if we talk about space, it can be introduced in the two different ways. The error in the satellite clock and error in the satellite orbit. Then when we talk about like when the signal will pass through the atmosphere, it will be like introduced error because of the ionosphere, troposphere, and then at the receiver noise because of some thermal noise and other noises which are present in the atmosphere. And when we reach a signal will reach at the receiver side, we are having the error something called as antenna phase center error because of the antenna of the satellite. Then we have multipath error and the receiver clock error. Now we will see those errors in detail. So the first error which is introduced in the space segment, and in that we have these two errors, the satellite clock error and the orbital parameter error. So this orbital parameter is error is introduced because of the non-spherical nature of the Earth gravity, because it is not same at every point. So if there is a change in gravity, the signal will see some variations and the speed or like it will reach early or late. And apart from that, the attraction between sun and moon will also affect the gravity, which will also disturb its orbit. So here we have given this Keplerian parameter which defines the uh, any like orbit of any particular celestial body. So using those parameters, we can find out that how to model this ephemeric error if there is something gravity or something if they are changing. So how to change introduce that thing. So whenever we get the data from the satellite, it sends us the data of all those Keplerian parameters, which is like true anomaly, then the inclination angle, ascending node, longitude of ascending node, argument of periveries. So all this data it will send us to you through the navigation code. Then we have this second one is the satellite clock error. So satellite clocks are made up of cesium and rubidium, which are having the accuracy of 10 raised to minus 12 seconds. So still we have some error introduced because of that. Then if the broadcast clock correction is not used by the like whatever the correction parameter that satellite is sending, if we are not using that, it will introduce a error which will play a largest bias part in the bias or error budget. And so what we can do is to correct this satellite errors, the navigational message, we are having some of the coefficients such as AF not AF1, AF3, TR. So those we can use, see this FE, A. So those are the orbital parameters. So using those parameters, we can find out the satellite error and then we can correct it our observations. Then, when signal is propagating from space, the first error which is introduced is due in the ionospheric layer. So, ionosphere is a dispersive medium, which means that it bands the radio signals and it changes the speed of the signal which is coming to us. So, here it passes through the various layers of the atmosphere and it is reaches to the receiver. So, what ionosphere does is like it speed up the signal. So, basically, it reduces the propagation time and signal will reach before its actual time, and sometimes it also slow downs as well the at the same amount. So majorly it will speed up the propagation, but sometimes we see the slow like retardation of the signal as well. So it all depends on the high total electron count which is available in the ionosphere. The second one is the tropospheric error. So troposphere is error is because of the various molecules of water and the other gases which are present in the troposphere. So as the like signal will travel through the troposphere or the particular environment, then it will like refract, and because of that refraction, it will bend as it will move towards the receiver. And you can see here the this one, the red one is the actual signal, but because of the refraction which is happening, the signal bands and it receives to the GPS receiver after some time. So which includes the like which delays the propagation time, which increase the propagation time compared to its actual time, and then we have to detect this kind of error. So here also you can see if the satellite is at our 90-degree or we can see at zenith, then we have to not have any kind of refraction because it's like exactly on top of us or top of the receiver. But as it is moves towards the horizon, then it has to cover more distance, and because of that tropospheric error will be high during that time. And it also depends on the amount of moisture available in the atmosphere or the other gas which are available in the atmosphere. And it delays the carriers and basically same as code as well, and it is a frequency dependent. So according to the scattering or the we learned during the remote sensing part, so depending on the size of the wavelength of the signal which is coming and the particle size, it will scatter and refract accordingly, and then it will affect the signal. So measured satellite to receiver range will be longer than the actual range, basically this retardation. Then we have the errors at the receiver end, which is also known as a like receiver segments error. In that, the first error is the multipath error. So multipath error is when the signal is reaching to the receiver, it will like have collision with the different objects such as the houses, tree, or nearby objects. Because of that, it will like go in the different paths and then will receive it after some time at the satellite receiver. And because of that, this multipath error will generate because of the traveling of the signal in the different particular paths before reaching to the satellite receiver. Then we have antenna phase center variation and the offset error. So this error is the technical error which avoids because of the design of the antenna. So if your antenna is in such a way that it will not directly capture the receiver, but it has some multipath error. So because of that, or the point at which the signal is received and the point where the center of the antenna is there, if both are different, then also we will face this kind of error. And generally it does not coincide with the geometric range of the satellite. So it varies depending on the elevation and the azimuth angle of the satellite, as well as the intensity of the observed signal. As the result, additional range error range can be expected. And then we have some noises, thermal noises, dynamic stress also, which are available in the nearby atmosphere environment, which also cause the receiver noise. And then we should use the signal to strength ratio, that what is the signal strength which we are receiving. If the signal strength is good, then we should consider that particular observable for our users location calculation. Then we have one more error, which is a cycle sleep error. So cycle sleep is a discontinuity in the receiver continuous phase lock on a satellite signal. So that discontinuity can occur because of the power loss, or because of the failure of the receiver software, or the malfunctioning of the satellite oscillator, or because of some obstruction such as building, trees, etc. as well. So this solid objects also prevent the satellite signal to come, and that's why, because of that, under those circumstances, satellite signal, after that the obstruction is like not there, it will reappear, so we will get the signal back. But during between, like, we will not get any signal, or we have some spikes or we jumps in the cycle which we already calculating, so that is known as a cycle sleep error. So now we will see like how the actual GPS data which we are receiving at the receiver will look like. So this is one of such data sets which I have collected during my bachelor's, when I worked with the like IRNSS GPS receiver, where we collected the data from this echoed receiver. And then so this work is done at the nearby university during my bachelor's. Uh, Here what we did is, like, we put one receiver to collect the signals from the uh, basically IRNSS system, and then we are interested at that time in calculating the tropospheric and ionospheric delay and other modeling. So when we get this kind of data sets from that, with that the first few lines will say about the what kind of format this data is having, what is date at which you are getting. This is observations file which is generic in nature, or you have navigational data, so that thing you will get. Then you have the different satellites which are available and their observation types, whether it's a carrier range or the pseudo range. And then G is GPS, I is IRNSS satellite. So at that time, 8 satellites from IRNSS were available, when from GPS 4 satellites were available. And then this is the sound to noise ratio, which will be useful to measure the strength of the signal. So if that ratio is like less greater than 25 decibels hertz, so it will be like 1, so quality will be 1. Higher the value, like 9, higher the signal quality, or higher the signal to noise ratio, higher the strength of the signal, which is good for us for calculation of the user's position. And then we have some data related to like approach. So approach means the at different time interval, what is the information that we are getting. So after that, we can see that it will give us the first of all day, year, month, day, hour, minutes, seconds, and then after satellite ID and other informations. So the first line is representing the approach at time at which we are getting the data. Then this is the satellite ID. So this is all the from GPS satellites, and then this one will be from IRNSS satellite. And here you can see this is the range which we are getting, which we discussed earlier as well, that code pseudo range or the phase pseudo range. So we'll get that range for or we can also see this is like coordinates of different satellites at x, y, and z coordinate of the satellite. and we have the receiver's coordinates, like we have x1, y1, z1, and the time, and then the signal strength, and this is the like strength of that signal. So 7 is representing that particular class. And similarly here we are getting the data from two different bands, L1 and L5 and S band. So this is from two different bands, the same coordinates of the satellites. Then we have this is known as the navigational data sets. So this is the IRNSS navigational data sets. So which includes the information related to the ionospheric error. So these are the para coefficients which can be useful to find out the ionospheric error. Then we have the time correction parameters as well. Then we have this different numbers are there which represent the following informations which we have given here. So the pseudo random number, year, month, day, hour, minute, second. Then these are the parameters that will be useful as we discussed during the satellite clock correction parameters, F0, F1, F2. So then the second line will represent the this satellite orbital parameters. So you can see that the parameter which we saw under the Keplerian parameters, all those parameters is given by one. Then some of the broadcasting parameter to find out the range of the signal. Then the satellite health related ID also, and some things like this. So that like how our signal from the space will look like. Now, when we see the error budget, so what kind of error can contribute into GPS? If we see overall, then we can see here that it can have first satellite clock error, which can introduce the error of 1.5 to 3.6 meter. Then we have orbital error, which is like less than 1 meter. Then we have ionospheric error, which is like 5 to 7 meter in range. Then further we have some errors because of the troposphere, which is zero point 0.5 to zero point 0.7 meter. Then we have the errors because of the receiver noise, which is zero point 0.3 to 1.5 meter, and then multipath error, which is zero point 0.6 to 1.2 meter, and then selective availability, which was now it's not there, so we do not have any error because of that. So basically, most of the error is introduced by the satellite clock. So we have to remove it using the correction parameters and by the with the navigation data. Then also from ionosphere, that error is modelable. Depending, we can see the content of electronic content which is available. Or if we use the dual frequency receivers, we can take the difference between two observations and we can remove this ionospheric error. So in general, like we can remove this big errors which is introducing because of the satellite clock and ionosphere, and then we have some minor errors. So out of that also we can remove the errors because of the troposphere by calculating the amount of gases which are available in troposphere, and we can model it, but we cannot remove this effect because of the multipath and the some of the times this receiver noise as well. Now, how to improve this error? So basically, we have to see some situations where, we have to see the satellite geometry, how the satellite is arranged in the sky space while collecting the data set. So if the satellites are distributed equally, like you can see here, then we can see here the over like connect like intersecting point of all these four will be like small one. But if the satellites are like near to each other, then we can see this connecting point is not a just point, it is a kind of rectangle. It means the uncertainty is high of getting the actual location. So basically what this principle is known as a dilution of precision. So basically if you have four satellites, you connect it with the like line with the user and you will find this kind of cone. So 1 upon volume of this cone will be like your DOP value, or you can also see it as a dilution of precision. So higher this volume or lesser the DOP value will be like good for uh, good measurements or finding the good positions of the satellite. So now when we see the solution which we received earlier, the error like a change in the position will be like B transpose B minus 1 inverse of it, then B transpose delta P. So here B transpose B inverse will considered as a dilution of precision. and then this sum of this diagonal and their root will considered as a geometric dilution of precision, which can be divided into two parts. So the first two components are the components related to the horizontal, and then one is related to the vertical. And if we consider all the three, then will give us the overall position dilution of precision. So we it is like divided into the positional DOP, which includes the horizontal and vertical dimension, and this fourth dimension is representing time. So this one is the like error in X, error in Y, error in Z, and the error in time. And then like how our satellites will look like. So if I at these locations, then how if I want to do GPS survey, so how to plan the survey. So basically, I will see that how many number of satellites are present at that particular time, and if the number of satellites are high, so I will try to do the survey at that time only. And the second thing, like our DOP value, dilution of precision, should be minimum while doing this GPS survey. So I will find out the time as well where this DOP value is minimum. Then we have this concept of differential GPS, which will allow us to do some of the correction and to improve the accuracy of the satellite. So here what is known as we know some of the stations, and then we have some stations where we do not know the location, which is the unknown position, where we will call it as a rover, and where we know the location, it is considered as a base station. Then first of all, we'll put our receiver at base stations and we'll find out how much error is there at base station, and that error we will apply at the rover stations. So that we will do, and then it error provides service. So it's like say, other thing like apart from this DGPS, we can like do the corrections using satellite based augmentation systems, S bars. And then there are like 3 4 systems, like we have our Gagan, then this VAS, which is wide area augmentation system, and then we also have IGNOS, which is European Geostationary Navigational Overlay System. So basically 3 systems are there, which is for satellite based augmentation system, which also find this errors, and then it distribute that error into the our observation. So basically this is the base station where we actually know the location of this particular point. So whenever, let's say, we are getting any point, we already know the x1, y1 and z1 of this particular point. And then from GPS receiver, we will get as a location parameter as a x2, y2 and z2. So now what will happen, that first of all we will find out how much error is there in all those 3 dimensions by doing it x1 minus x2, y1 minus y2 and z1 minus z2. And whatever error I will get, I will record it as a delta x, delta y or delta z. Now when I will find the coordinate for this point, let's say coordinate for this point is x3, y3 and z3. So now whatever error I got here, that error I will introduce over here. So I will now, my new coordinates will be like x3 plus the error delta x then y3 plus delta x y, and then we have z3 plus delta z. So now we will put that error so that we will already get the correction for that particular location. So basically it will remove the error which is like common for both. So what will be the common? So the point like atmosphere through which like these 2 points are very near to each other. So when the signal is coming from the satellite, the ionospheric error will be similar for both. So the ionospheric error it will remove. Then tropospheric error will be same for both the points. So tropospheric error it can also remove. Now what else it can remove? So if the data is coming from the same satellite, then it can remove the error because of the satellite clock as well. But the error because of the receiver clock we cannot see like correct, because here the receiver clock error will be something else, here the receiver clock error will be something else. Similarly, multipath error will also be change, also like it will also change along with the nearby object or topography. So we cannot also correct the error because of the multipath or receiver clock or the nearby geometry. So we can correct the errors because of the ionosphere, troposphere, orbital parameter of the satellite. So those kind of error only we can correct over here. So apart from that, orbital error also. So errors because of the orbital parameter. So those errors we can remove here. Now see one of the example that here the satellites constellation is there, space segment, and here at the receiver we are getting the actual ID like coordinates as a x plus 3, 30, y plus 60. But here the GPS receiver like site, or we can see the S bar site or any site which is giving the correction, where we found out the actual location is x plus 5, y minus 3. But we see the actual location of it is x, not x plus y only. So this plus 5 and minus 3 are the terms because of the error. So we have to remove minus 3 and we have to add plus 3 to make it x plus 0, y plus 0. So that error which we got delta x, which is minus 5 and plus 3, we will add over here into these two. So 30 minus 5 and 60 plus 3. So we get the final reading as a x plus 25 and y plus 63, which will give us the actual coordinates of the receiver after the correction. So this is the, if we see the Survey of India site, they are having their own continuously operating reference system, which is also known as a course network, which provides this kind of satellite based correction while doing the GPS surveying and other surveyings, so that we can use those correction parameter and we can improve our GPS accuracy. Now, when we talk about this accuracy, so what do you mean by accuracy? So all of you are might be following this Paralympic games right now. So where we have archery or shooting games, we can see that people are shouting like putting the shots over here exactly in center, which is also known as a bullseye. So if your points are exactly on center, it means it is high accuracy. And all those arrows or the points or locations where you put markings, if it is like closer to each other, then it is also known as a high precision. So it means this is considered as a high accuracy, high precision. But now if I take this example where these points are located near to each other, it means precision is high. But overall these points are away from the center. It means the accuracy is less. Similarly, if I see here, so points are near to this circle, it means it represents high accuracy. But precision is not good because it is like spread it away from each other. So precision is low. Similarly, here if we see, so here it is not neither near to the center, neither they are concentrated with each other. So we will get low accuracy, low precision in this particular case. And you can see here that if we use the normal GPS, our data will look like this, where like this is our actual location and this is the deviations in the x and y direction which we are getting. So this is the positive deviation, negative deviation in x direction or the east direction, and then this is positive and the negative like difference or the error in the north direction. But when we apply this DGPS concept, so you can see now the error got reduced and all the points came closer to each other, which is showing the high precision and high accuracy compared to over here where the precision and accuracy both were less. So we have improved the accuracy and the precision by improving the DGPS positioning. So now after this, we will discuss some of the numericals. Before that, I will give you a break of 5 minutes, and then after we will start at, 5 minutes. So now we will start discussing the question and answers. So we will see some of the questions from the previous year assignments and some of the from the same some courses on GPS surveying by J&K Ghosh. So we'll see some of the questions from there as well. So first question is, which of the following can indicate the correct set of GPS segment? So here we know that when we talk about GPS, it has three different segments: space segment, user segment, and control segment. So here we do not have any segment known as a navigation. So option one is wrong, second one is wrong, and the fourth one is also wrong. So we just have control, user, and then along with that we have the third component, which is a space component. So for space segment, so our option is the right option here is option number C. Then we have our next question, which is the fully operational GPS satellite constellation comprised of. So this is like here we are talking about the GPS system by USA, which requires around 24 satellites, okay, which are like which is useful for finding out the final locations, like in full constellations. Then the frequency of P code, which in GPS receiver, so which is 10.23 megahertz. Then we have the standard positioning system. So SPS, and then we have restricted positioning system. So what is the true about this thing? So first thing, this standard is useful for the civilian purposes. So this option is right, where it is not useful for military, because for military it is restricted positional system is like useful. Then the what is the horizontal and vertical accuracy? So it has the horizontal accuracy of 100 meter, while the another one is having around 30 meter, 20 to 30 meter. This military, which we use for military purposes. That's why the option A and option D is correct over here. Then we have this WAS, which is wide area augmentation system. So how much satellites it consists? So it consists of 25 ground stations and two geostationary satellites, which broadcast the various correction parameter while doing the GPS surveying. Then we have in absolute positioning method, the SPS user, it means standard positioning system. Users can get an accuracy of 80 to 100 meter. We will get in that. Now, which is the source of the GPS error is in SPS can have more than 1 meter of error. So we know that in ionosphere we have the error because of that, and the error because of the satellite clock is also more than 1 meter. Then we have this multi-path error is maximum for which is multi-path means is the its collision with the different so if the depending on the wavelength we can see that whether CA code, which is like in 1 point something bits is having, which is because of that it is having maximum error, where the ionospheric error is minimal for the CA code, multi-path error is maximum for it. Then we have the space segment gets interfered to user segment through. So we talked about this thing in the starting of the lecture, where we introduced that satellite communication is like two-way between the space segment and control segment, whereas it is a one-way ranging signal between the control segment and space segment and user segment. So fortunately, it's in like so we can know that now it is a one-way communication, but in it is using the L band. So that's why the L band one-way ranging signal radio frequency. Then the third one, in case of GPS positioning, the position of blank are considered to be the objects at a known position. So we already know the position of the satellite because we know the x1, y1, z1, x2, y2, z2 for all the satellites. We consider whatever like at least 4 satellites to find out the location of user. So that's why the here the answer is like the position of satellites are known. Position of satellites. The next one is like Blank types of observables are present in the GPS signal. So we learned that it is having two different kinds of observables. One is the code pseudo range and then one is a phase pseudo range. So the answer is 2 over here. Then we have a blank is an additional error associated with the carrier phase pseudo range in comparison to those associated with the code pseudo range. So which error is associated additionally in the carrier phase? So in carrier phase, there is an error called as integer ambiguity, which is like error in calculating the number of cycles. So basically, this is like one cycle, and then if we missed out because of some signal loss or some other reason, so the error in the counting of this number, which is known as integer ambiguity, so that error is only associated in the carrier phase, because in code phase we are using just a directly time parameter. Then we have during the GPS observation this dilution of precision. So lesser the dilution of precision, higher the spreading of the satellite, which gives the perfect location, which means it should be minimum for the GPS survey. Then we have most significant systematic error in GPS observable is because of the uh, ionospheric error and then the receiver clock error. Both are high. So if it is just one, then this like most significant will be because of the receiver clock. Then we have this ionospheric error is minimum for this is CA4C L1 frequency. So L1CA in general, if we talk about, then it is lesser for L1CA. The parameters for computation of satellite vehicles position is obtained from navigational data. Now we see some other example questions that component of GPS signals that gets deciphered by all type of GPS receiver. So which is like obtained by all receivers. So we know that the CA code is useful for the civilian purposes. That's why it is deciphered by everyone. But if the question is like which of the GPS signals can be transmitted by L1 and L2 both the carrier waves, then your answer will be like precision code, because this CA code is like transmitted with L1 frequency only, where the PY code is used transmitted by L1 and L2 both. But in terms of receiving by the users, CA code is a civilian code which is like collected by all the type of receiver, whereas PY code is a restricted code which is like highly useful for the military purposes, and all cannot decipher that particular code. Then we have this for 3D positioning. Global Navigational Satellite System (GNSS) requires minimum of how many satellites? So we need four number of satellites. One is for X direction or the X location. Then one is for resolving Y. One is resolving Z. And then the fourth one is resolving the time parameter, because to avoid the timing error because of the satellite clock and the receiver clock. So we need, that's why, four satellites for resolving the data. Then we have this basic objective of Nowstar GPS is to provide the service for. So we know that it provides the positional, navigation and timing. So option number B. Then we have that which of the following gets mitigated by DGPS positioning. So basically we already know that whatever the error is common between the base station and rover station, that will get nullified while doing this DGPS positioning. So in that, like multipath error is the near to the receiver, so it might be different for both the stations and the receiver, so it cannot be mitigated by DGPS. Similarly, cycle sleep is also because of the nearby object, so it cannot be mitigated. Similarly, topography error will is not also be like can be not be removed because it depends on the local condition. So only error which is like ionospheric error, tropospheric error, or orbital error. So whatever related to the atmospheric parameters that can be mitigated by the DGPS positioning. Then we have the satellite-based Nowstar GPS augmentation systems are. So we learned in the first slide only that IGNOS, VAS, and Gagan are this kind of augmentation system where DGPS is just differential GPS positioning system, global positioning system. Then what is true for this? So now star GPS consists of minimum 24 satellites, so this is true. Then precision of GPS positioning is being defined by its standard deviation, so that is also true. Then the GPS methods provides more accurate 3D position than the relative static position, so that is not true. Then the like GPS observation from geostatic GPS receivers provides less accurate position than the GPS code receiver, so that is also false. So the first one and the second one is right. Then we have this uh, the next to identify the correct statement. So for accurate GPS positioning, GDOP value should be large. So it should not be large, but it should be as minimum as possible. It is minimum. So this DOP value should be minimum. So instead of large, if it should be minimum, then this option will be correct. But right now it's a large, so that's why this option is incorrect statement. Then the second one is the integer ambiguity is associated with the carrier frequency. So we learned that it is related with the carrier only, not the code pseudo range. So that is true. Then GPS is a one-way ranging system. So that we know that it is a one-way for user, it is a one-way, but between control segment and spread segment, it is a two-way. So if we talk about user, then it is a one-way. So that is also wrong, and this one is right. So correct option will be B and C. Now we will see the next one, which is like during the GPS surveying, the initialization of rover receiver is required for which method? So it is required for relative kinematic method and stop and go method, where we like stop, we'll just there will be one station which is once a base station, and then we will take different readings and go stop and go. Will not put that stations for long duration. We'll just take a reading and go. So their initialization of rover is required. First, once we require like initialization is done, we can do the survey. Similarly, in the relative kinematic also it is required, whereas in static methods it is not required. We'll put it for a long time, and then we can correct it using the nearby stations as well. Now we have the next one is like GNSS stands for Global Navigation Satellite System. As of today, which of the following is the complete set of GNSS? It means which one of the following provides the global coverage. So we know that GPS is from USA, which provides the global coverage. GLONASS is from Russia, which also provides the global coverage. Galileo is from Europe, which also provides the global coverage. BeiDou is from China, which also provides the global coverage. So the option C is incorrect. Then the IRNSS, it is a regional system. So this is not correct. This is not correct. So the correct option will be the option number D. So this is IRNSS from India, which is regional navigation system. QZLS is also a regional navigation system from Japan. And these three are the satellite-based augmentation system, not the GPS system. This is considered as a S-bus, not as a GNSS. So that's why those three are also not correct. Then we have the next one, that basic premises for using the DGPS technique is to reduce the error due to. So when we use the DGPS, we already talked that we can reduce the atmospheric error. Then we can reduce the error because of the satellite orbit. Then satellite clock. Satellite orbit we can reduce, and then we can use satellite clock. But multipath we cannot do. Similarly, receiver clock we cannot do. So the correct option will be B. Then we have the next question is the orbital period of the GPS satellite is determined by the, so it is determined by its semi-major axis. Then which form of the following method is widely used by the GNSS constellation to distinguish the satellite from each other at GNSS? So that is code division multiple access, which is known as CDMA. Which then the next one is which of the following statement is concerning the GNSS error is correct. So here we can see that tropospheric delay increasing with the humidity. So tropospheric delay basically depends upon the molecules which are present in the atmosphere. So it means the higher the molecules, the higher the tropospheric delay. Then ionospheric error. So that option is correct. Then we have the ionospheric error is highly correlated with the position of moon. So that is wrong because it depends on the number of electron content available in the ionosphere. This moon will affect the orbital error or the satellite orbit error. Then the multipath error is caused by the building and man-made features and not by the vegetation. So that is also wrong because it is caused by all the nearby objects, whether it's a building, vegetation, or any feature which is natural made topography or man-made feature. And then the last one is the observed range is called as a pseudo range because of its erratic nature. So it is not giving us the actual range, but it is giving a range with some error, which is not correct. That's why it is known as a pseudo range, which is a false range. That's why option A and D are correct. Then we have some numericals over here. So I will give you, so what we have to do is here, we have GPS satellite is flying at a distance of 20,000 kilometers from the observer. So we have to find out the phase difference here. So just, I will give you 2-3 minutes. Try to do it by yourself and then we'll discuss. So now we will try to do this question. So where what we have to do is we have to find the phase difference here. So what we will do here is like let's say we have waves which are coming from the satellite is like this. So this kind of range is coming from satellite to receiver. So let's say if this is the receiver is over here somewhere. So we can see this over here it is completing one cycle, second cycle, third cycle, and then this fourth cycle is like half only. So the phase will be like 180 degrees. So here you can see this is the phase 0, then 90-degree phase, then this is like 180-degree, and then we have similarly 270 and 360 degrees. So if it is completing the full cycle, then phase will be 0. If it is like in between, then we have to find out the phase associated with that particular wavelength. So here what it is given is like the distance between these two is like 20,000 kilometer. So distance between this and user and receiver is 20,000 kilometer. Now what we can do is we can divide it with the wavelength and we can find out the number of complete cycles. So what is n? So for that what we can do is we can do the like if you want to find out n, so we can do n is equal to total distance divided by wavelength. So when we want to find out the wavelength, so we know that for wavelength c is equal to f lambda. So here for lambda it will become c by f. So here we have this d which is 20,000 convert into meter also. So we have 20,000 into 10 raised to 3 meter. Then we have lambda is equal to c by f. So c will be 3 into 10 raised to 8. Meter per second. And then we have frequency, which is 1575.42. So we can just write 42 and we can just write the back 10 to the power 2. So, megahertz, so we'll convert it mega. So okay, we just write 2 10 to the power 6. And then here we have, let's say we will move this point towards over here, or we'll just remove it 10 to the power 2 and we will keep. So now we will just simplify this. So 6, 7, 8, 9, 8 into 10. So we have this cancel with each other. This 1, 0. This. And now we will simplify this thing. So now we will see that 2000 into 157542 divided by 3. So if we do this thing, we will get something like number of n is equal to 10502880000. So it means the n what we got is integer value, not in the fraction. It means it is completing all the cycle, and that's why our phase will be 0 over here. So that's why we will get 0 as a phase, 0 degree. So that is the solution of this question. Now the next question is the range accuracy with a microsecond accurate clock in GNSS receiver is about 300 meter. Now, if we improve the clock accuracy to 3.3 into 10 raised to x second, then the range accuracy becomes 1 centimeter. So we have to find this value of x. And here in the hint, it is given that error-free range is equal to speed of light into time of the travel. So we can see this in the first case, the error-free range is, let's say, 300. So we will write 300 into speed of light, which is 3 into 10 is to 10 to the power 8, and then time, which it took. So our time over here is 10 to the power minus 6. So similarly, we will do it for improved accuracy, which is for which the time is 3.3 into 10 to the power x. So here in this one, then the corresponding range accuracy is 1 centimeter. So 1 into 10 to the power minus 2 meter. So error-free range is 1 into the 10 to the power minus 2 is equal to speed of light, which is 3 into 10 to the power 8. So we have 3 into 10 to the power 8. And then we have our time of travel, which is 3.33 into 10 to the power minus x. So now we will solve this equation and we will find the value of x here. So first of all, we will make this 3 into 3.33 will become around 9.99, which we will consider as a 10 only. So here on this side, we will get 10 and then 10 to the power 8, so it will become 10 to the power 9. Here we have 10 to the power minus 2, and into here is 10 to the power minus x. So if we simplify this thing further, we'll get minus 2 is equal to 9 minus x, and then we will put x on this left hand side, and then x will become 9 plus 2, which will be 11. So the value of x will be 11 over here. Now the next question is which of the following option best describes the uncertainty in the measurement? So when we talk about uncertainty, it includes the both random errors as well as the systematic error. So that's why the option number D is the correct option over here. Then we have the distance was measured between this 200 as like 200 meter plus or minus 0.1 meter. So the relative position of this measurement is how much? So we just have to see how much 0.1 of 200. So just we'll get the 1 is to the 2000. So basically you can just do something like this: 200 divided by 0.1 divided by 0.1, basically divided by 200, which will become 2000. Then the next one is which of the following mathematical principle is applied for finding the geographic position on the Earth's surface using the GPS. So the name of that concept is trilateration, which means that we know the distance between the receiver and the satellites, and then it will give us the final location. So that is known as a uh, trilateration. Then which of the following is not a segment of GPS? So GPS is best control and user segment. So we do not have anything known as a launch segment. So we will remove this particular thing. Now the next one is the dilution of precision. So DOP value in GPS is based on the satellite geometry, which we discussed, that it should be distributed equally in all the direction. If it is too close, then the uncertainty in finding the position will increase, and that's why this DOP value should be minimum at every time while doing the GPS surveying. And how many Navstar satellites are necessary is 24. Then we have this: which of the following factors are responsible for ionospheric delay in GNSS observation. So for ionosphere, the total electron count which are present in the ionosphere, it is responsible for this ionospheric delay. So the option first option is correct. Then the carrier frequency, it is also correct, like L1, it has very minimal ionospheric delay. At L2 it is high, and then the receiver will not make any effect, or atomic clock will not make any effect on that, so it is not responsible. So then we have this: which statement is correct out of the given four statement. So course, which we discussed by mission by ISRO of India, which is like continuously operating reference stations, so can be used as a reference base station, so that is true. So the option A is correct. Then reference receiver should record the observation for longer period as compared to the rover. So that is also true, because it has to be proper, find out the error properly. So that is also true. Then remote receiver must always be placed on the known location. So that is wrong. Rover will be placed on the unknown location, while base will be should be put on the actual location. So they should not put on top of each other. The next one is: which of the following error is or R is corrected in the DGPS? So we know that the tropospheric delay, orbital error, and ionospheric errors are like resolved or mitigated in the DGPS surveying, while this atomic clocks will not be carried out. But if it is written just atomic clock here. If it is mentioned that satellite or receiver clock, then we can see satellite can be mitigable, but receiver clock cannot be mitigable. That's why that option is not correct. Then we have two different terminologies, triangulation and the trilateration. So triangulation, as the word suggests, we have three triangles and we using angles, we find out the measurements. Whereas in trilateration, we have the dimension of three dimension of length. So using that concept, we find out the dimension. Sides are measured basically. So in the first one, angles are measured. In the second one, sides are measured. So for this option C is right, whereas D is wrong because both are opposite to each other. And the triangulation is useful in the plain areas, like where we can see the sorry, it's like good for in the hilly areas. As in hilly area, we cannot measure the distance well because of the slope. So that's why trilateration can be preferred in the plains area, whereas triangulation in the hilly area. So that's how we will wrap the question answer session of this GPS. And now we will see some of the practical sites which can be useful to us in doing the GPS survey. So one of such site is like you can write something as GNSS plant. So basically we'll see one the particular site is from Trimble and then some of the other sites as well. So we can look into it. So before that, I will give you a break of 5 minutes and we'll back after 5 minutes and discuss about that thing. So now we will start learning about this GNSS planning or how to plan for GPS survey. So we will start with this GNSS mission planning site. So here you can see this is like particular GNSS mission planning site. Just click on begin planning, and then it will ask you like your locations and then where you are or where do you want to do the survey and all those things. So you can mention those details. Let's say I want to do the survey at around 23 latitude and 75 longitude. So it will put me somewhere. You can just change your point for some other locations as well. Then search results. Then after you can specify the height at which you just want to consider the satellites or satellites which are in the some range that only you want to consider. Then at which date you want to do the survey that you have to specify, and then at which time to which time you want to do survey. So that you have to specify, and we can also specify our time zones as well over here. So in any site, first of all, you will apply those kind of thing that where do you want to carry out survey, at which time you want to carry out the survey. Then after it will show you the once the process is done, it will show you the amount of satellites which will be available during that time, then amount of satellite based augmentations which are available. So you can see this entire list you will get. So from GPS you will get how this many satellites. Out of this red color, it means this satellite is not healthy satellite. Then the green means the satellite is healthy, so you can use it for the observation. So currently we are getting the data for GPS, GLONASS, Galileo, BeiDou, QZSS and SPAS. We are not getting any data from IRNSS. So then after you can click on any of the satellites and you can get the like details about it as well. So you can just click on select like which you want to use, apply. Then it will calculate the how many satellites will be available, DOP values, elevation, visibility, sky plot. So different parameters it will calculate based on that. So here you can see the DOP value is like very less for this is GDOP, geometric dilution of precision, PDOP value, HDOP value, and VDOP value. So you can see like when this DOP value is less, then the second one is like the number of satellites available. So you can see that at which particular time, how many total satellites are available. So 25 satellites from BeiDou, 3 satellites from QZSS. So we cannot use direct like only QZSS because only 3 or satellites are available. So we have to use the integration of more. So SBAS 10 available, Galileo 7 is available, GLONASS 8 is available, GPS 13s are available. Then their elevation, that how far that satellite is there, which will determine the geostationary or geosynchronous nature as well, depending on their altitude from the user. So we will get that data as well, that what is the elevation and that how that elevation is also changing. Um, then we have the visibility, that whether the satellite will available for how many time, whether it's will be available for entire time during the survey. So let's say you are trying to do survey between the 11:30 to 5:30 p.m. to 5:30 p.m. So during that time, will the satellite will be available entirely if you are considering any particular satellite or not. So that thing you can also find out. Then you have the sky plot, which will represent like in the red like it's a round, and it will show you that how many satellites are available, which one is near to you, which one is far away from you. And then you also have something related to the world view, where it will show you that how the satellite will move during the survey, so you can make an animation out of it also. Similar, in the starting of the lecture we have seen the same thing in this Trimble GNSS planning. So this is the main site like people use for their like GPSS planning. So it is Trimble, which is also called the GNSS also. So here the good thing is like if you see go to the charts along with the elevations and number of satellites, DOP values, it also provides the ionospheric information that how much ionospheric delay will be there, and then because of that how we can model the ionospheric error. So that kind of operations are also available. So basically you can see ionospheric delay will be like maximum during the like morning to afternoon times, and after that it will decrease, so that we can find out like at which location how much the ionospheric delay as well. So you can like see how it is changing. So this is total electron content available in that particular column. So that is like you can find out, and based on that like whether the scintillation is minimum or maximum, then ionospheric index you can find out and do the survey when then it is minimum. So you can find out the basically timing during which you can do this GPS survey, because what we need essentially for doing GPS survey, we need at least 4 satellite which will give you us the particular location. And apart from this 4 satellite, our next criteria should be like it should be available during entire the survey. Apart from that, the DOP value should be minimum, ionospheric delay should be minimum. We should do during that time when the tropospheric delay is also minimum. So we have to take those kind of measurements while doing the survey, so that it will give us the more accuracy while doing the survey. Apart from that, to remove the error or to reduce the error which we have seen in error budget, we can use a technique like DGPS, or we can use the corrections from course network or from SBAS, and then we can also correct our data according to that, and we can improve our accuracy from that as well. So now what we will see is, so that's like how we will wrap up our GPS session. So in the next class, what we are going to do is we will solve some of the questions related to the given week, and after we complete that, we will try to solve some of the questions, or we will just try to look into QGIS software, which is uh, software for geospatial data processing. So right now, just we'll discuss about this software a bit. That QGIS is open source software for managing, storing, analyzing geospatial data sets. Then we have some other source software known as RGS, but it is commercial. This is for commercial use. You have to purchase it, whereas this QGIS is open source software. And there are so many plugins are available. As it is open source, people are writing the different plugins, different utilities they are integrating with this QGIS, whether it's related to the hydrology, infrastructure, network analysis. So people are generating the different modules they are attaching with the QGIS, which you can also use over here, which will increase your efficiency. So to download the QGIS, you have to go to their QGIS website. Uh, and then you can go to the downloads, and you can go downloads. So skip to and go to downloads, and either you can download the long-term version, or if you want to download the particular version, so you can go to the archives. So here you can just go down. So you can see that if you want to find out the long-term releases or the some other previous versions if you want to download, so you can just go there also. And if you can just write on Google also that QGIS, let's say I want to download 3.16.9 version, so you can just write 3.16.9 version download. 3.16.9, so it will open this kind of index library where they have stored all of their earlier versions. So from here, like you can select the QGIS 3.16.9 version for the Windows system. So you can just go and check it for Windows. And then you can just find out the version 3.16.9 setup cross 86.exe, and This is for 32-bit system and this is for 64-bit system. So you can click on this and you can download the QGIS into your system like this. Further, if you just click that and just install that in your system, just click OK, 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 and next and finish. After that, if you want to download the uh, exercise data, so simple sample data, so that also you can download from this. So you can go to the data, go back and go to data, and then you can just go to their site to download the data sets. So you can also download the QGIS sample data sets from here, and then manual exercise data also you can see, and training manuals also you can download. So you can, apart from this main downloads, we have the manuals and then other things. So what we can do is you can go to resources, we can go to documentation, and then we can go to this here that how to install QGIS, how to integrate it with Python. So all those things, PyQGIS, how to use QGIS in Python, which is like direct version PyQGIS, and some versions like manuals are also there in English and other language. So you can also go and check into out, like user guides are there. So you can just, if you want to learn, you can just read those manuals or the handbooks and just try to get information from that. But in this class, we are going to do some of the exercise with the hands-on data from India and from the region outside the India, and we'll try to put our hands on that using the hands-on session where you will perform along with me. So this is kind of manual will look like, which concludes that, like includes that how to start with QGIS, then how to work with different vector data, raster data, mesh data, vector tiles, 3D tiles. So GCP, GPS data sets. So GPS those data also it provide it like that if you collect any data from handheld GPS, then how to import the data into QGIS, and then how to connect basically within the QGIS device. So those things also you can do it over here. So basically, I mean, whatever we see, like how many satellites are available, signal strength, psi plot, that you can also see this different DOPs value, horizontal accuracy, vertical accuracy, lat long. So all those things you can set here as well, and then we can use it for different data sets. We'll analyze different data sets in the upcoming lectures, and we'll see the in detail. So basically, we'll look into it. Then there is a tools known as a plugins. So plugins are the various small tools which is generated by different communities or different persons. So you can go and check out like which kind of plugins are available in QGIS, and then you can install your own plugins also. Now what we will do is we will see that how the window of QGIS will look like. So on your screen just write QGIS 13.16.9 version. So why I am insisting to install you this version, because in this version we can easily run the tools related to the hydrology and other thing, which is not possible in the updated versions because there is a issue with the compatibility of the Python version which this 3.16.9 uses, and the Python version which this hydrological analysis tool requires. So because of this discontinuity and the discrepancy in the Python version, I request you to use the 3.16.9 version so you do not have any issues with when you work with the QGIS for hydrological analysis and some other analysis as well. So once you will open your QGIS, it will look like this. If you have already worked on some projects, so it will look like this. So I will click on new empty project and we will see the basic layout of QGIS. So you can see this is the data panel where your data, you can, whatever data you will import, it will be visible over here. Then this is the various toolbox which is available to do different tasks. Then this will be like browser where you can find out the files and you can open the different folders from here. Then whatever data you will put, it will come under this layer panel, and here are the different tools. So if you are not able to see any of the particular layer or panel, you are not able to like view it. So you can go to view and you can go to panels or toolbars, and you can just click on this checkbox, yes or not. So if you are not able to see browser panel, which is over here, so you just go there and just check on there. If you are not able to see this processing toolbox where the tools are there, so you go to this panel and just click on this checkbox where this processing toolbox is written. So it will open up this thing. So if you're not able to see same screen similar to me, you can do something like dragging and dropping, and then also you can put your uh, tools like here. So you can just mount it over here wherever you want to put. And if you want to remove, you can remove also. And then now if you want to edit afterward, you can go to view panel, and then I want to add layer panel. So it will be over here. If you want to just keep it separate, just keep it separate like this. And then just change it like this. So it is a separate. So like this, you can arrange your QGIS window like you, whatever way you are comfortable with. Similarly, when I talked about plugins, so you have this plugin menu. You can go to manage and install plugin. So it will open up a new window for you. So which will look like this. So these are the different plugins which are available. So you can, this is for making the animations. Then this is for calculator. This is for attribute based clustering. So you can see different plugins are there. You can use that. Some plugins are there also for downloading the remote sensing data sets. Then this is for automatic waterfall detectors. So like that, you can see what, like if you want to do with some particular work, and if like tools are available for that, you can just install that tools and then use it for your purpose. Some let's say if we see something related to the machine learning or something is there or not. So for if you see the machine learning, then we have the tools related to this map toolbox to extract the real life object from the satellite imagery with the map flow by GeoAlert, which provides the AI-based mapping pipeline, which detects the roads, fields, forest, and so on and so forth. So this kind of tools will be available, which you can use. So deep neural remote sensing, deep NEC. So this three type of things are there which you can use and install the plugin. So that is like about the rough overview of QGIS. So in the next lecture, we will try to first we will try to solve the numericals or the MCQs on the upcoming week, and then after we will try to solve like hands-on session on this QGIS, where we learn that how to import the different types of vector data and raster data, what is the difference between raster and vector data, and what other kinds of data are available in the QGIS. So we will see the different data sets and how to import all those data sets, whether it's the CSV file or the geospatial file. So how to import all those things into QGIS window. So we'll learn about that, and then once we are comfortable with that, we will see that how to prepare a map using the data which we have added into QGIS. So basically our overall objective is to prepare a map out of the data given to us. So how to prepare a good map, so that we will learn, and if time permits, we will see some of the applications on the georeferencing as well, georeferencing and digitization. So that's what we are going to do in the next lecture. So by that time, please install the QGIS into your system, this specific version 3.16.9, as we have highlighted today's class. And I will highlight, give you the data session, data also in the question answer discussion session, so that you also download before the lecture. So that's it. Thank you for joining. We will see you in the next class. Thank you, everyone. Good night.